The fire environment is a complex interaction of many elements. This training program is designed to assist you in understanding how to monitor the fire environment. We will examine the 7 fire environment factors you should monitor on the fire line and look at visual and measured indicators for each of these factors. When you look up, look down, and look around, you will recognize the indicators that will allow you to size up the fire environment. Then you can anticipate problem fire behavior. In this first unit, we will discuss fuel characteristics and the indicators you can use to assess how the fuel characteristics will contribute to problem fire behavior. Fuel characteristics change very slowly with time, but fuel types can change over a distance as a fire spreads. You should look at the fuels that are burning and the fuels adjacent to a fire in order to anticipate potential fire spread and intensity. Which fuels support fire spread? Continuous cured fine fuels provide a good carrier fuel and will allow a fire to spread rapidly. On the other side of the fuel scale, heavy accumulation of larger dead and down fuels is an indicator of possible intense burning conditions. An accumulation of dead and down fuels can cause a fire to burn over a large area for a long duration. Look for this condition in older age vegetation and areas that have hosted thinning and logging operations. These first 2 indicators show the potential rate of spread and potential for long-duration burning. Next, consider the fuel characteristics that lead to crown fires. Is there a well-developed fuel ladder for the fire to move from the surface to the crowns above? Conifer reproduction and brush are common ladder fuels. Tree branches that hang close to the ground are another good ladder fuel. The lichens and moss that grow in many conifer trees can also contribute to this ladder effect. Once a fire gets into the crowns, tight spacing of trees or brush is required to sustain a moving crown fire. A rule of thumb for this indicator: look for crowns that are closer than 20 feet apart. High winds or steep slopes can cause a crown fire to move through more widely spaced vegetation. There may be special conditions in a fuel type that require your attention. One of the first you should assess are the firebrand sources. This will help determine how severe the spotting problems will be. Firebrand sources can be different in every fuel type. Standing rotten snags can offer an unusual way for a fire to spread. Snags provide both a good firebrand source and a fuel that is receptive to firebrands. Beware if a fire has burned through the surface fuels and left the canopy preheated or scorched. This will cause the vegetation to dry out and become more flammable. Bug kill, frost kill, or diseased vegetation can make available an enormous amount of fuel that is not normally flammable. Remember, every fuel type can have some unusual fuel condition. Red slash in the northwest. Low water tables in the swamps of southern Florida. Draped pine needles in manzanita brush stands of northern California. Or the special hazards in the urban-wildland interface. These are just a few examples. When in unfamiliar territory, ask local firefighters for information. Put yourself in the place of this firefighter, headed into the first shift of a fire assignment. What do you see when you look at the fuels on a fire? In this second unit, we are going to discuss fuel moisture and its indicators of problem fire behavior. Fuel moisture determines if fuels are available to burn. This factor can be measured. You can also feel it. Fuels of different sizes dry at different rates. Fine dead fuel moisture content changes continually and quickly on a daily basis. Larger dead fuels and live fuels change more slowly. All fuels have moisture content levels which will indicate dangerous burning conditions. Relative humidity is one of the most critical indicators available on the fire line. The fuel moisture content of fine fuels is driven directly by relative humidity. Dangerous burning conditions start to develop when relative humidity drops below 25%. This indicator can vary depending on the region you are working in. For example, in Alaska, relative humidity readings of 30% are considered low. Relative humidity can be measured. Fire line supervisors should carry a belt weather kit and measure relative humidity several times during a shift. Following correct procedures is important. An incorrect reading can be worse than no reading at all. The other size class of fuels that play an important role in carrying the fire are the small sticks and twigs, less than 1 inch in diameter, the 10-hour fuels. Dangerous burning conditions can develop when these fuels drop below 6% moisture content. This 10-hour fuel moisture content is measured by the fuel sticks at the fire weather stations. Again, this indicator can vary depending on the region you are working in. When you are on a fire assignment, there are several ways to get 10-hour fuel moisture content information. The fire behavior analyst on a large fire should know this and may include it in the shift briefing. Even if such measured information is not available, you should be able to feel how dry these fuels are. Grab small twigs and branches as you travel into your assignment on a fire. Are they easy to break, or do they just bend? Learn to sense the condition of the fuels. The large dead fuels, 3 inches and bigger, are affected by both normal seasonal drying and by persisting drought conditions. Be aware of any drought conditions that exist. This will give you a head start in figuring out how dry the large dead fuels are. Once again, as you travel into your assignment on a fire, learn to sense the condition of the fuels. Break open a few large, punky logs and feel for moisture inside them. When you arrive on the fire line, look at the large dead logs. Do they only partially burn, or do they burn all the way down to ash pits? Making these observations can help you figure out how dry the larger dead trees are. Seasonal drying will affect the moisture content of all fuels. As you look at the condition of fuels on a fire, Determine how far along the seasonal drying has progressed. The fines, such as needles and leaves on the ground or grass, usually dry first, followed by dead and down sticks and logs, and then live fuels such as trees and brush foliage. As seasonal drying progresses, fuels that could not support a fire previously will become available to burn. Now let's look at a fire where a major firefighter entrapment occurred. The Butte Fire burned on the Salmon National Forest for over 6 weeks during July and August of 1985. On August 29, the fire made a major run in a side drainage of the Salmon River Canyon. This extreme fire behavior overran about 1 mile of fire line. The firefighters working on the division where the fire made its run were preparing for a fire operation along an indirect fire line. 73 firefighters were forced to deploy fire shelters during this fire run. There were 3 other hand crews on this same division that did not deploy fire shelters. They were able to move to a safety zone before the fire hit. What were the crew supervisors of these 3 crews observing that allowed them to make this decision in a timely manner?
Several factors influenced our actions. The previous day, we were also on this division, and as we visited with the branch director and our division supervisor, our indications to them was that of concern, that drop point 28, due to topography, due to the winds that we had experienced, due to the weather factors, low humidities and high daytime temperatures, was not a good place, that there was a possibility, great possibility, that great fire intensity could occur. We continued to work in that area and monitored weather.
I started taking weather readings around 1 o'clock and came up with RHs in the high 20s, and we decided to break for lunch, and when we got RHs of around 20%, we talked and decided it'd be best to pull on all the way out rather than to this safety zone that was below us, below drop point 28, or even this safety zone. We decided it would be better to pull completely out of the timber and up into the clear cut to the north of drop point 28.
Earlier that morning, about 10 o'clock, we identified the fire activity is increasing, and at that time we identified plumes developing in the Wallace Creek drainage and Sourdough Creek drainage. At that time, it was evident that the fire activity was on the increase, and as we broke for lunch and Fred took the weather readings and the humidity started to drop, we could also see
In this third unit, we will discuss the indicators of the last factor used to monitor fuel conditions. Fuel temperature affects the amount of heat energy and time it takes for fuels to ignite. Solar radiation determines fuel temperature. It can be felt and measured. Hot days reduce the amount of energy required for ignition and cause the air near the fuel to be drier. This will increase the potential rate of spread. With the same air temperature, areas that receive continual direct sunlight will have higher fuel temperatures than areas that are shaded. On a 90-degree day, the temperature of ground fuels in direct sunlight can be as high as 160 degrees. You should also look at the aspect of a slope when considering fuel temperature. Watch as the sun passes overhead. As the day progresses, these slopes will go through changes in being shaded or in direct sunlight. As a result, there will be changes in the flammability of the fuels during the day, depending on the slope's aspect. This is a good indicator for fuel types with a high percentage of fine fuels. Look at the fire behavior on two slopes with different aspects. In the first situation, the fire is burning in grass and sagebrush on an east aspect of 0900. The fuels on this aspect will normally have the highest fuel temperatures in the morning, as the arrow indicates. In the second situation, the fire is burning on a west aspect, in the same fuels at 0900. Fuel temperatures on the east aspect were near their peak at 0900. But as you can see on the graph, fuel temperatures on this west aspect will still be increasing well into the afternoon. How do you think the fire behavior in the two situations will compare by 1500 in the afternoon? Topography and its indicators are what we will discuss in this unit. This element of the fire environment helps to influence the rate and direction that a fire will spread. Terrain is constant, usually changing only over the course of many years. Terrain can change quickly over a distance as a fire spreads. You must scout out the terrain where the fire is burning and understand how it is aligned with wind in order to understand how fast and in what direction the fire will spread. A fire responding to steep terrain has been a common denominator in many firefighter fatalities. Steep slopes can cause rapid rates of spread by increasing flame contact and heat transfer to new fuels. In addition to rapid uphill runs, spotting from rolling firebrands is a concern on steep slopes. Box Canyon. And chutes are terrain features that have convective or channeling effects on air movement. This is often referred to as the chimney effect. A fire that moves into the influence of a chute or box canyon can exhibit a dramatic increase in its rate of spread. Saddles are terrain features common on major ridges. It is not unusual for rapid uphill fire runs to be pushed into and through a saddle with an increasing rate of spread. Narrow canyons are another terrain feature that you should be concerned with. A slope reversal can occur quickly when a fire backing downhill reaches the opposite slope and begins a rapid upslope run. Also, narrow canyons allow fuels on the opposite slope from a fire to become preheated by radiation. Spotting can then occur quite easily with any flare-up. Watch again how fire responds to the terrain features. What is similar about the fire behavior in all three situations? We will now look at the weather leg of the triangle. Weather works with topography to influence fire spread. Wind is one of two factors that concerns us about weather. We will discuss wind and observation of its indicators in this unit. Wind is the primary factor that will determine a fire's rate and direction of spread. This is important enough to repeat. Wind is the primary factor that will determine rate and direction of spread. The first and most obvious indicator is the presence of moderate to strong surface winds. Wind leans flames over, which increases flame contact and heat transfer to new fuels. Additionally, wind provides a mechanism to transport firebrands. Sustained surface wind speeds above 10 miles per hour can generate rapid rates of spread in many fuel types. You can estimate the wind speed by using the handheld wind gauge provided in the belt weather kit, or by using the Beaufort Wind Estimation Scale as a guide. A light breeze of 5 miles per hour can be distinctly felt on your face. Flagging will flutter. A wind of 10 miles per hour causes single trees in the open to sway noticeably. At 15 miles per hour, you have a moderate wind. Dense stands of timber sway, and dust is raised on dirt roads. Sustained wind speeds exceeding 20 miles per hour can cause inconvenience walking against the wind, tree damage, or minor structural damage. The next wind indicator we will consider are lenticular clouds. These lens-shaped clouds forming above a nearby mountain ridge tell you that there are strong winds aloft in the area. When moderate to strong high-level winds blow over mountain ridges, a mountain wave wind pattern is set up. The indicator, lenticular clouds, form over the crest of the mountains. The lee side of these mountains can experience unusual downslope winds if this pattern drops to the surface. High, fast-moving clouds are an indicator of a change in the weather pattern, shifting winds in particular. Take special note if these clouds are moving in a different direction than the surface winds. Cold front passages have been responsible for many erratic and extreme fire behavior events due to strong, sudden wind shifts. Usually, cold fronts provide a squall line of thunderstorms as a visual indicator. These fronts approach quickly. During the course of a cold front passage, winds will shift from the southwest to the west or northwest. And the wind speed will increase. Winds will become strong and gusty for several hours as the front passes. What do you think about working the right flank of this fire? Towering cumulus buildup is an early indicator of thunderstorm development. This buildup can progress to a mature thunderstorm in as little as 30 minutes. This is a mature thunderstorm. Notice the fuzzy-shaped top and flat bottom. When the cumulus buildup reaches this mature thunderstorm stage, violent downdrafts can occur. Sometimes you may observe virga from the bottom of the thunderstorm. This indicates that downdrafts have begun. The downdrafts from a thunderstorm are the result of air falling rapidly downward from the storm's center. When this air hits the surface, it fans out in all directions, causing strong, erratic surface winds. A thunderstorm passing near a fire can produce a sudden increase in fire behavior. Another wind event that we need to discuss is the föhn wind. There are föhn winds in every part of the country. These winds are one of the most critical fire weather situations confronting fire line personnel. A föhn wind can last for several hours or for several days. Winds of 40 to 60 miles per hour are not uncommon. These winds are accompanied by lower relative humidities and higher temperatures. It is important that you are able to anticipate the wind shifts that can result from the interaction of föhn winds with local winds. These wind shifts will have a sudden adverse effect on fire behavior. This is one example of these wind interactions. This is a situation that occurs along the coast of Southern California. The föhn wind is pushed aloft in the day by the diurnal sea breeze blowing upslope on the coast range. A fire burning in the area will be under the influence of the diurnal sea breeze. Note the smoke column. As the sun begins to set and the diurnal sea breeze begins to die down, the föhn wind, or Santa Ana, is allowed to surface. This can produce a 180-degree change in wind direction, with much lower humidities and higher temperatures. This reversal of conditions can happen in a matter of minutes. The indicators are subtle. A sudden calm should be one of the first warnings. Watch for a smoke column that wavers back and forth as the winds battle with each other. These indicators will tell you a wind shift could be coming. At some point in time, the föhn wind will break down and the diurnal sea breeze will reestablish its influence. This can present another dangerous wind reversal situation. Many firefighter entrapments and fatalities have been the result of unanticipated sudden wind shifts. Observe what the winds are doing at all times. You are watching fire behavior on the Painted Cave fire that burned on the Los Padres National Forest in June of 1990. One individual was killed, and over 700 structures were destroyed in the Santa Barbara area. This fire moved extremely fast. It was reported at 1800 to be about 3 acres in size. By 1830, it had traveled 2 miles downhill. What would cause a fire to burn downhill at such a rapid rate of spread? In this unit, we will discuss the second weather factor, atmospheric stability and observation of its indicators. An air mass that is unstable or in transition from stable to unstable provides the potential for a fire to develop vertically and grow rapidly. Unstable air masses are associated with good visibility. Another good indicator of an unstable air mass are gusty winds or dust devils. Cumulus cloud formations are also associated with an unstable air mass. The appearance of cumulus clouds arranged in lines indicate unstable air at high levels. When these Castellanus clouds are observed in the morning, there is a high probability of thunderstorm activity in the afternoon. The smoke from a fire can also be used as a stability indicator. Smoke that is rising straight up to a great height in the atmosphere indicates an unstable air mass. An inversion is caused by a stable air mass. This results in smoke collecting in a layer just above the fire. Fire behavior usually decreases after an inversion. In the inversion just seen, there may be a zone of warmer, drier air that forms during the nighttime hours. This zone is known as a thermal belt. When a fire enters the thermal belt, you can expect some increase in fire behavior. When an inversion does start to lift or break, that means the air mass is starting to become unstable, and you can expect a significant increase in fire behavior. You're going to watch time-lapse photography of fire behavior on the Ship Island fire that burned in the Salmon National Forest in July of 1979. There will be a sequence of 3 successive days shown. The sequence begins on July 24th. It is 1000 in the morning, and you're looking at an inversion over the Parrot Creek drainage. It is now early afternoon. Notice the spot fire in the bottom of Parrot Creek. By 2100 that evening, the fire had made its run through all of Parrot Creek and has slopped over into the next drainage, Tumble Creek. This is July 25th. The camera is on at 1000, and you are looking at an inversion over the Tumble Creek drainage. The fire actively backs downhill all day with occasional strong upslope runs. The fire has established itself well into the Tumble Creek drainage by 2100. This is July 26th. The camera is on at 1100, and you are again looking at an inversion over the Tumble Creek drainage. At 1400, there is a spot fire just across Tumble Creek in the bottom of the drainage. "22 firefighters deployed fire shelters on this incident. 1 firefighter was killed. and another burn. Were there any indicators of unstable air mass conditions during this 3-day sequence? We have looked at all legs of the fire environment triangle for indicators of problem fire behavior. But there is one more factor, the fire itself. Fire behavior increases in observable stages. Its indicators should not be overlooked. The first fire activity you will see as you go on a fire assignment is the smoke column itself. A column that is leaning before the wind and not rising indicates a wind-driven fire. This is usually associated with rapid rates of spread and short spotting. Another type of smoke column to be concerned with is a sheared column. This is a column that rises straight up, then at some level is sharply sheared off in a horizontal direction by winds aloft. This wind shear provides a mechanism for long-range spotting to occur. In addition, these winds aloft could surface and affect the fire. A third type of smoke column to look for is a well-developed column. This indicates intense burning is taking place and unpredictable fire spread in any direction can occur. Look for the capped top, similar to towering cumulus clouds. Strong downbursts are associated with this type of column. Feeling a light rain or sudden calm under this type of column is an immediate indicator of downbursts. A transition of the smoke column is important. When the color of the column changes from light to dark, or when the column starts to rotate faster, it means the fire intensity is building. Once on the fire line, you begin to watch the fire activity itself. One of the first indicators you should notice as the fire behavior increases is intermittent single tree torching, progressing to groups of trees torching. If this occurs, the stage is set for a transition to an active crown fire. Another early indicator is when areas that were only smoldering start to get more active with longer flame lengths and begin to spread. The presence of small fire whorls means the fire is beginning to develop vertically. These fire whorls also provide a mechanism to transport firebrands. Pay attention when you're getting frequent spot fires. When you're getting spot fires faster than you can pick them up, you are witnessing problem fire behavior. As fire enters the realm of problem fire behavior, it will display several of these indicators. By now, you're probably hearing the freight train, as the noise of a fast-moving fire is sometimes referred to. You should have already established escape routes and safety zones to use. Do you see indicators of problem fire behavior in the fire that you are now watching? You have been watching fire behavior on the Eagle Fire. This fire burned on the east side of the Sierra Nevada mountains in Northern California in July of 1989. 5 firefighters were overrun by the fire while trying to pick up spot fires in advance of the main fire. 4 were burned, 1 severely. What you have done in these 7 units is observe indicators that you can use to anticipate problem fire behavior. When you can anticipate problem fire behavior and adhere to the fire safety guidelines, you will be able to select safe and effective tactics to use on the fire line. Remember, look up, look down, and look around.